Now we come to section 8.4, and it's a more interesting section. Here we'll be interpreting point cloud images to extract planes using PCL methods. We'll learn how to downsample, select a point cloud patch, extract the plane, and display corresponding points. So we're going to use many methods to find the plane, and our main file will be this one right here, find plane pcd file.cpp. Okay, so overall this is what the file looks like. We include the headers. We're going to create various point cloud types for the original point cloud, for a downsampled point cloud, then for another kind of filter point cloud, and one for selected points that we're going to select from the user, and then finally the output, the last output with the plane. We're going to load this point cloud from file, so we need to load it. We're going to create publishers for many of these point cloud types, and we also need the equivalent sensor messages for them. Here we're going to use voxel filtering to downsample the original cloud. This will be important to make the number of points fewer and increase the efficiency of the algorithm running on the computer. We're going to instantiate a PCL utility object, which in turn will instantiate a few other things, but this is what will allow us to interact with the point clouds. We'll ask the user or wait for the user to select a patch of point clouds, and from there we call another function that has a number of steps that computes the plane. So find plane PCD file will eventually called find indices of a plane. Notice that, let's say we have a table and we estimate a plane from a number of points that are not exactly all at the same height or all at the same level. So we need to do a few computations to extract what we think is the best plane for that. After that, we can return that pose. Visually, the code looks like this. We're going to get the original point cloud, maybe Baxter with a stool and a Coke. We downsample the point cloud so it's not as dense. We have less points here. We're going to maybe select a patch of points on the stool. This is the stripped version with no robot here. Then we're going to do a coordinate transform of the points from the camera frame to the plane frame. We're going to then do another pass-through filter that maybe is just looking at the local region of points, not at the whole image. And finally, we're going to publish the plane. How do we start? First, we're going to create all the point clouds that we need for all the different operations. The first one is going to be this PCL connect. That's XYZ RGB. In fact, all of these are XYZ RGB except the one where we select points by the user. So this is going to be our input point cloud. Then we're going to have that downsampled point cloud. A little bit later, we're going to have the box filtered point cloud, and eventually I think we'll have this one as the output plane points pointer. After we do this, we load a colored point cloud from file, so we use the input output class, load PCD file, we use the XYZ RGB type. This F name is something the user will input into the terminal, and then we will select these dereferenced pointer as the variable to save the input point cloud. because we want to visualize many of these point clouds, we'll need to create publishers and corresponding messages for them. All of these are point cloud 2, and we have these topics, the PCD topic, the planar points topic, and the downsampled PCD topic. So the first major operation we're going to do is voxel filtering. You'll also get to try this at home as a homework. Here's the link to the tutorial. The first thing we do is create a voxel grid object and pass the correct point cloud type. So here we have voxel grid with a XYZ RGB type, and we call that the vox object. Then we can call these three methods on vox. Number one, set the input cloud. So we want to pass the right point cloud. This is the input point cloud that we computed earlier. Secondly, we set the leaf size. This is the extent of downsampling that we want. The larger this number, the larger the downsampling. And finally, we want to output the filtered point cloud. So we use filter and pass the dereferenced pointer to do that. So now downsampled connect pointer has the downsampled version of the point cloud. If we want to publish that, we then convert from PCL to ROS. And so we use to ROS message and use this ROS type right here. The next thing we want to do is get a copy of the selected points chosen by the user using the RViz plugin select points. So this file, this method will be waiting for the publication of the selected points by the user in RViz, and once those points are selected, it will place them in this selected points cloud pointer. If we go inside of get copy selected points, we'll see that we already have a structure called PCL selected points pointers with the points. This particular variable or member is obtained during the callback of this program. So this is waiting for the selected points. Once we click on them, we publish the data, the callback gets called, and then those points get saved into this variable in the callback. Here we can extract the size of the points and save it as an int. We can also just copy the header. So we access the member header and paste it over or copy it over here to output cloud header. We do this for frame ID. We do a direct assignment, camera depth, optical frame. This is a workaround for a bug and publishing selected points. But this is the frame we will input in RViz when we want to see these point clouds. We copy the isDense flag. The width is equal to the number of points, and then height is equal to 1. So this is the metadata, and the actual data is done down here. We take outputs, points, and resize it to the total number of points that we selected, and then we go through a for loop where we want to copy the data. The way we're doing that here is using getVector3fMap. This method is copying the XYZ point and returns what is called a PCL vector 3f map. The vector 3f map is nothing more than a type def for an eigenmap of eigenvector 3f's. So at the lowest level, we're using a three-dimensional float vector from eigen, and it's a map of these. So we have a key and then the value, and so these get this function right here is basically returning the vector here. So by taking PCL selected points and calling this method, we can also copy that over here. In the PCL utils select callback, we're going to call the function fit points to plane. So we have the patch that we have selected by the user, and we want to know what is the approximate plane of that patch of points. We're going to use the same technique that we introduced in lecture 5. If you remember, covariance can be computed through this equation. So you may have your vector of data and multiply it by the transpose version, or do the outer product. And once you do that, you need to subtract basically the mean from each one of those points. In matrix form, it is done in this way. So programmatically, we can compute the outer product of the vector and then subtract the centroid from each of the points. Once we have done that, we can compute the eigenvalues and eigenvectors of the covariance matrix to obtain what are the major and the minor axes of the plane, but also the normal of the plane. And this operation is this one right here, where we are subtracting the centroid. So this is the way it is computed and then removed from the points. The centroid, by the way, is basically acting as the mean value right here. The covariance computation is this outer product. And then to extract eigenvalues, the first thing that we do is create this eigensolver as a three-dimensional matrix initiated with our covariance matrix. Once we do that, we can call eigenvalues, just the real ones, which should be all of them, for this matrix. The next step is to select the eigenvector whose eigenvalues are the lowest, and this is pointing to the normal plane. Why is that? Because the smallest variation that we expect on a plane is going to happen within the context of our scene in the z direction, or in the vertical direction. So here we're going to go through each of the three columns, 1, 2, 3, and we're going to save the value or the eigenvalue to this variable, and we'll keep the smallest number. So if lambda test is smaller than minimum lambda, this we initialized as something, then we want to keep that number, so we copy that to minimum lambda, and then also keep that index as a record. After that, we extract the eigenvector and set it to plane normal, so we compute the eigenvector for a column I normal, and just take the real part of that and set it this way. So we do this to find the minor axis and then also the major axis. So this or I should call this the smallest eigenvector, which is going to be equivalent to our normal, and then the major axis will be equal to the eigenvector that is the longest in the plane, like so. The third column will then be pointing to this other axis of the plane. Once we have that plane, we want to extract the indices of the point clouds on that plane, just the point cloud indices of the point clouds. So we call this function. We have our input point cloud here. We have the patch of selected points, and then this will return those indices. This method, find indices of plane from patch, actually has a number of important calls. We're going to use compute point normal, which returns the normal parameters for a plane and also the curvature. So you can look at the tutorial here, but basically by selecting the nearest k neighbors, we can get an idea of the normal plane for those points. The parameter k is important because if it's too small, we might get some noise or some disturbance here and not get the true normal. For curvature, we're using eigenvalues, where lambda 0 is less than lambda 1 is less than lambda 2, and this gives us a sense of curvature. And you can see here that wherever we have a yellow line, we have high levels of curvature. We're going to be interested in transforming our point cloud. Maybe originally it has a coordinate frame over here, but we want to change it to a different coordinate frame. For us, we'll change from the coordinate frame in the camera to the coordinate frame on the plane. We'll also do a pass-through method where we'll choose the direction of filtering and then apply the filter so we only look at a desired location. So within the find indices method, we want to compute the parameters of the plane. So we pass in the patch cloud, and from there we're going to get the parameters that describe a plane as well as the curvature. Once we have these parameters, we can use them to approximate the equation of the plane, but even more to get the frame of that plane. Now, if you imagine the camera pointing down on the object, we want to have a coordinate frame on the plane because most of the points on that plane will have a z-axis or a z-value that is close to 0. If the coordinate frame is on the plane, x will vary, y will vary, but most of those will have a z-value close to 0. And then, so we know that, and we also need to decide whether the normal is pointing towards the camera or away from the camera. So the convention will be that the plane normal will point towards the camera. And so by having these plane parameters, we want to get a transformation. To do that, we call make affine from plane parameters as part of this class. And what that is going to return for us is the transformation for the plane with respect to the camera, or another way to think about it, going from the camera to the plane. So once we have this transformation, we can use the method transform point cloud. This will effectively change the XYZ values of all the points to use the new transformation. So here we're sending in the input cloud pointer, but we also want to output the new points to the transformed cloud pointer, and here we need to pass in that transformation and call the inverse of that. Okay, so now all of those points have a z-value that is near 0. The last thing we're going to do here is the pass-through filter. We're going to call the pass-through class, give it a XYZ RGB type, and call it the pass object. As input, we're going to get this transformed cloud pointer, and then we're going to further say we want to filter around z. We know that most of those z-values are close to 0, so we set those limits from negative 0.02 or 2 centimeters in the negative direction and 2 centimeters in the positive direction. We can finally output the filter to the indices variable. Okay, and so then we would just get a very clean picture of the plane. To test the code, we're going to use the Coke can cloud point image or file. This is found in the PCD images package or folder. So let's get our setup going. So down here we're going to start ROS core. We're going to start RViz as well. Then we want to load the file, so let's change to the images package. We're interested in cokecan.pcd. So here we're going to run our code, run PCL utils, find plain PCD file. As soon as we do that, it will request the name of the file, which we now have here. And it's going to output some interesting information. It says I have started voxel filtering. The number of bytes in the original cloud is 307,000, but afterwards it's 7,876. If we come over here to RViz, we'll see that we have a number of point clouds. Let me see, I am missing this one. Sorry, the right frame is camera depth optical frame. And then we can come over here and select the PCD cloud. At first sight, this doesn't look like it makes much sense, but if you rotate it correctly, eventually you'll get to the right angle. Something like this, and then we can zoom in and then appreciate the Baxter robot sitting in front of this Cocan with the stool. And so it's a more interesting scene. Right here in the point clouds to display, we can change the size of the pixels, which can affect the way that this looks drastically. So now we can run the find. So we've run the find plain PCD file. What we're doing now is just waiting for us to select a patch of point clouds. To do that, we need to add this plugin for RViz, publish selected points. Click on it, and then select a particular set of points right here. As soon as we do that, we can look at the output of this terminal. So here we see received a new patch. We got about 1,002 points. We compute a centroid, XYZ centroid from those points. Then we get the major axis vector. So this is along the x-axis primarily. And we get the plane normal, okay, which has this vector component. And we then copy those point clouds and then compute the transformation with respect to the camera rotation. Okay, this is the rotation, and then this is the origin, and then all of these points are getting transformed. Finally, the number of points passing through the pass-through filter is this one, and we can look at different topics to see how those point clouds look. So the downsample topic, you can see, is just a lot more sparse. And then the planar points is just giving us these surfaces right here. Now let's see if we can rotate this a little bit more in a different direction, maybe like this. If you can see, all of those points are located exactly on the same plane. Yeah, the best way is to appreciate them like this. So that's what we're getting from our computation. Oh, so here's those instructions, how we select them, and the output. So I hope section 8.4 was interesting to you. Please take some time to look at the details of the code. I prefer to just look at the highlights in the presentation for the sake of time. But here you should be able to learn how to use all these techniques then to approximate planes on points. Thank you very much.